So Pasha, will you use the board behind?
Yep. Yeah.
So maybe we'll test the sound delivery. Do you have a microphone with you?
Yeah. Okay. Well, can you hear me now?
Yes.
Okay.
But I'm not sure if you slightly away from the screen.
No, I mean, that's how I'll be talking. Okay, can you hear me?
Yes.
Oh, okay. Yeah, I'm okay.
Yeah, we will start on time.
Sure.
Within. Okay, I'm very happy to have Professor Pasha Pylyavsky from University of Minnesota in our seminar. And today he's going to talk about crystal invariant theory. So Pasha, it's all yours.
Okay, hi everybody. Thank you very much for inviting me. Okay, if at any point something's unclear, I mean, for example, I hope I write large enough so you can read the board, but tell me if I don't do it right. But okay, so this is based on joint work with Ben Brubaker, Gabe Frieden, Travis Scrimshaw, and Thomas Lamb. And sort of, I hope to first give like a bit of introduction to crystals and geometric crystals, at least the kind we will need here. So I hope to start very slow. So please ask me if anything's unclear. I actually want you to understand everything I'm saying. And also, this is like 8 a.m. here, so I'm a bit still sleepy, so I may not be as agile at the beginning as one would hope. Okay, let me just start. So let's start with so-called basic SLN crystal. That's another problem. This crystal just looks like, so I will kind of define crystals by example. I will keep saying more and more about them, but I will not give just definition like from scratch because it would take too long and not be very helpful. So just go with me as I show you, like start with this basic example. So the basic SLN crystal is just crystal on is certain graph connecting objects like this. You have a row of certain lengths and you fill it with numbers 1 through n like this in a weakly increasing manner. Okay, so you have all possible ways to fill it like this with numbers 1 through n, and then those are connected to each other by crystal operators. And the rule is that crystal operator EI tilde changes last I into I plus 1. Right, so for example, if we pick n to be just 2, and if we pick a row of length 2, then the picture would look something like this. This guy, now we apply operator E1 tilde and changes the last one into a 2. So we get this thing, and then we apply it one more time. It changes it into this thing. And that's it. There is no more ways to fill a row of length 2 with numbers 1 and 2 in desired way. So if we try to apply a crystal operator one more time, strictly speaking, we would say that this thing just maps into 0. Okay, so this is a very small example of basic geometric crystal. Are there any questions about this? Okay. Now, there is something interesting you can do with them. You can kind of create more complicated crystals out of those by taking tensor products. So let me show you the tensor product construction. So tensor products. Right, so you start with several of those single row things, and there is some way to define a crystal which is their tensor product. And again, so the rule will be something like this. When operator EI wants to act on the product, it has to choose in certain way on which factor to act, and then it acts on this factor. So I will again just show you by example how it would look like. So let's take the guy I just had over here on the board, right, with 3 vertices. And let's tensor him with himself. So if we had, here's a copy. Oh, sorry, this should be 1, 2, and this is 2, 2. And similarly here. So this will be my first copy of this crystal. This is the second 1, 1, 1, 2, 2, 2. And then the set of vertices is just a Cartesian product of this set and this set. So you have vertex like y1 tensor 1, 1, etc. 1, 1 tensor 1, 2, 1, 1 tensor 2, 2, 1, 2 tensor 1, 1, 1, 2 tensor 1, 2. Okay, I'll just fill it out. 2, 2, and 2, 2 tensor 1, 1, 2, 2 tensor 1, 2. Okay, so the set of vertices is sort of straightforward. It's just Cartesian product of this set of vertices and this set of vertices. The interesting question is, if I want to act by operators EI tilde, how do they act now? So in this case, let me just show you just the answer in this case. So in this case, something like this would happen. The only operator here is again E1 tilde, just because we are only filling them with 1s and 2s. And it would map things like this. This goes here, goes here, goes here, goes here, goes here, and this guy is by himself. So this is how crystal operator E1 tilde acts in this case. And you can see that what really happens is that in this arrow, it just acts on the second factor. In this arrow, it just acts on the second factor. In this arrow, it acts on the first factor. So each time it kind of chooses on which on which factor to act. And there's some rule according to how it should choose, but it would take a little bit of time. So there is something Kashiwara defined called epsilon and phi functions. And when you decide how it acts, you need to compare something like compare epsilon and phi functions of the first factor and second factor. And it wouldn't be too hard to explain, but maybe it would take us a bit away. So you should just know that there's a precise rule on which factor the crystal operator acts. Like there is some way to just compute something and decide, okay, in this case, it should act on this factor, and in this case, it should act on that factor. Okay, so far so good. Ask me if something's unclear. So we started with the basic geometric crystal. We take the tensor products, and now you can see that they split into connected components, right? In this case, there's 3 connected components. And this corresponds in the theory of symmetric functions on how, so the generating function of a single crystal or simple crystal is just what is called, so let me write generating functions. So if we take the single what I call basic SLN crystal of lengths I, length I. This gives you the so-called fundamental symmetric, or complete homogeneous symmetric function HI. Right. So in our example, for example, we had, here, let me write it here. So in our example, we had 1, 1, like this top part over here. It's 1, 1, 1, 2, 2, 2. You take generating function in the sense that this gives you x1 squared, it gives you x1, x2, this gives you x2 squared. And the sum of those three is equal to H2. This is a complete homogeneous symmetric function in two variables. Okay, so far so good. Okay, now, of course, when we take tensor products of those basic geometric crystals, it corresponds to multiplication of those H's, right? So if you have general tensor product, this corresponds to HI1. The generating function will be HI1 times HI2 times etc. And you could ask, what are those connected components? And if you've seen this theory before, you would guess that this is just how this product decomposes into some of the so-called Schur functions. Right, so each connected component of this product crystal, tensor product crystal, will be one of the so-called, the generating function over it will be a so-called Schur function. And for example, this picture over here proves the following formula. It proves that if you take H2 times H2, or H22, people call it, you get this guy will turn out to be S4, right? So Schur functions are labeled by partitions. So this here partition 4 plus S31, that's this connected component, and plus S22, that's this single guy over here. So the three connected components here are the three Schur functions you get when you decompose this product. And that's part of the original reason why crystals are so exciting in some sense. So this corresponds, you can think of it as taking two, giving you a rule of how to multiply irreducible, like highest weight modules for say GLN or SLN, right? So you can think of, so this gives you the so-called Littlewood-Richardson rule, how tensor product, and you can, like once you have those more complicated crystals, you can also take their tensor products, etc. And so in general, so you can just it kind of well, I could say more about it. So somehow, I think the goal was that let's say you take irreducible representations or highest weight modules of some semi-simple Lie algebra or Lie group, and you try to tensor them and decompose this tensor into connected component into irreducibles. So what ideally would happen is that you would be able to find a basis such that, you know, you pick a basis in one of them, you pick a basis in the other, and then just subs, like you take pairwise tensors of those basis elements, you get basis for the tensor product. And then it would be ideal if you just can say, well, this part of those pairwise products gives me one irreducible and this part gives me another. And it's sort of, one could aspire to find such a basis, and the closest one can come is the so-called canonical basis by Lustig and independently by Kashiwara, but it doesn't quite work. This property doesn't quite work. But what Kashiwara observed is that if you somehow do things modulo Q, so you need to first take quantum group, which is Q deformation of this Lie algebra or Lie group, and then do tensor things there, and then you somehow ignore things which have Q in it. You just take things modulo Q, then there is such a basis, and that's what he called crystal basis. But the remarkable thing is that whether you need to do one or the other doesn't impact the combinatorics in some sense. So you can still tell how irreducibles of the original semi-sample Lie algebra or Lie group tensor with each other and how they decompose, but by writing some kind of graphs like that. And that was the miracle of Kashivara's crystals. Okay, so just one more thing before I move on to geometric version of all of this. There's one more interesting thing you can do with it. You can compute something called energy function. Yes, there's a question. Somebody.
I don't think so. Someone just didn't. I need to mute them. Yeah.
Function. So there's something called energy function.
Maybe I can ask a question now.
Sure. Yeah.
So just for assurance, so do you mean that in terms of representation theory? So here, this picture is you take the tensor product of two three-dimensional module of which are highest weight module of SL2, and then decompose into three modules. So one is of dimension 5, one is dimension 3, and one is dimension 1 here.
That's correct.
Great, thanks.
That's right. Yeah. Okay. Okay. So, and one more thing. So there is something called energy function, which is defined for tensor products of such things, for tensor products of crystals. And it's just some algorithm. I will not tell you. I mean, it's not super hard, but I just don't want to spend time. And there's just a way to compute if you have a tensor product like this, or more long one with more factors. There is a way to compute something called energy of this tensor product. And it just ends up being some number. So in this case, if you were to compute it, you would see that over here, the number would be 0, over here the number would be 1, and over here the number would be 2. And now, instead of taking just simple generating function, you can also add a power of q, right? So in general, it will work out like it is in this picture, that on the same connected component, the number is the same, right? But it is possible to have different connected components with the same number. This example is just too small. In this example, all components have different number, different energy. But in principle, it's possible to have more like different connected components with the same number. But nevertheless, now that we have this number associated to connected components, we can use it as a power of q to put in front of those Schur functions, right? So like this guy would get q squared. This guy would be like, we take generating function of weight of this thing times power of q, which is q to the energy, right? So q to the 1, and here is just 1, right? Q to the 0. And if you do this, then you get something important. You get the so-called whole Littlewood symmetric function. Whole Littlewood symmetric function. Well, here it was h2 times h2, so it's whole Littlewood 2. And whole Littlewood functions they're important. They come up in many, like they come up when you study Springer fibers. They come up when you the specialization of McDonald polynomial. It's just in general an important symmetric function. So, and we will see this energy function in what I will keep talking about. So that's why I wanted to mention it. It will be something, an important example for us.
So will you give the precise definition for energy function?
I was not going to, but soon you will see precise formula in the rational case. And then if you tropicalize it, it will be precise formula in the usual case. So I can say something about it.
So for energy functions, only is defined for any crystal, or is only defined for some special class of crystal?
So I believe energy function is defined whenever you have tensor product. So if you just took a single crystal, if you don't think of it as a tensor product, it's just like this guy, so it's just 0 everywhere. But once you can kind of, if you have tensor of two things, you can measure local energy between them.
Mhm.
And if you have more than two factors, what you can do, you can somehow measure local energy between all pairs of factors and then add them up. And this ends up being, but there's also a precise formula which I can show you. But yeah, energy function is something you get once you start tensoring crystals. It doesn't exist for just crystal with like which is not tensored.
Mhm.
Okay. Any other questions?
Is there a categorified version to tell us what are the energy functions? Like you have a category and the simple modules has shifted gradients, and this in terms of instead of the usual multiplicity, these are graded multiplicity.
Let me see if I can say something intelligent. So there is a way to think about energy function, I believe, where you think you take some kind of central extension of the quantum group. So you get a bigger quantum group. And then you check by how the central extension acts on your modules, and it acts by like multiplying by q to some power, and this power is exactly the energy function. So there is kind of a very natural representation theoretic way to think about it, but it requires you to think about sort of there are different versions of quantum groups, and some of them are like central extension of another one, and then you see how the central element you added acts on things, something like that. So that's the closest I can think of what I can say intelligently about category where this makes sense somehow.
Okay, great, thanks.
Yeah. Okay, so now let's try to talk about the same story, but let's do geometric lifting of it. So it was Bernstein and Kazhdan who came up with this idea that you can somehow lift crystals from piecewise linear world to geometric world. So let me. So there's a general phenomenon in mathematics where if you have a formula written in a sort of piecewise linear manner, yes, it's okay. So if you have some formula written using operations of minimum, addition, and subtraction, you can replace it with formula where minimum becomes plus, addition becomes times, and subtraction becomes division. Okay, so it takes you sort of from piecewise linear to rational or birational or geometric world. And often people think actually in the other directions. It's called tropicalization, right? Well, some people call this direction tropicalization. Some people call the other direction tropical. So you can think of going from birational algebraic geometry to kind of piecewise linear algebraic geometry, and that's what people who study tropical geometry do. But in our case, we have crystals which happen already to be piecewise linear objects, and we will be asking the question of lifting them. So how does it look in practice? In practice, okay, here's an example. Let's say you have a formula, something like this: minimum of 2x and y minus z. And if you, so this guy gets mapped into something like x squared plus y divided over z. Right, so instead of x plus x, now we have x times x. So instead of minimum of those two things, we have their sum. And instead of y minus z, we have y divided by z. And this lifting is not unique, right? I mean, I could, if I change this plus to a minus, or if I put coefficient 2 here, it would still tropicalize to the same thing over here. But often there is sort of a nice choice of correct choice somehow of coefficients to lift to. Okay, so if you have never seen it, by the way, here's an exercise or puzzle. So I told you what happens to minimum, plus, and minus. What does maximum operator lift to, right? So if you have just max of x and y, what rational function of x and y it becomes? Okay, so if you want to something to puzzle over while I keep talking, then just, I mean, it will be just some simple rational function in the two variables. Okay, so this is the general phenomenon. Now, let me try to tell you how we can apply this to our basic geometric crystals and their tensor products. So first of all, the first thing we need to think about is the following. Whenever we have element of our basic geometric crystal, it looks like this, right? It's some filling of a single row kind of shape. We can parameterize this by just remembering those numbers. Let's call number of ones x1, number of twos x2, all the way, to xn. And now we can think of this thing over here as just a vector of x parameters x1 through xn. And now that we go to rational world, we will just again think of vertices of our crystal or points in our crystal as just vectors like this, except now we will ask those parameters to be just arbitrary real or complex numbers, let's say real numbers for now. So let's say those parameters are just not integers like they were here, but just real numbers. Those will be the points of our crystal. And now I need to tell you what are the crystal operators in this geometric world. So now we will have crystal operator EIC. And what is this C? So the C will be a parameter. It will itself be, a real or a complex number. And you should think of it as C is how many times we apply EI. Right, so in the piecewise linear world, we didn't think of it this way, but we always apply just a sort about applying a single time EI. But in principle, you could say, well, let's try to apply, E1 2 times. And then we would write it E1 2. So now in this rational world, we will also have EI applied C times, where C now will be not an integer, but again, a real or a complex number. Right, so we have, so strictly speaking, points in our geometric crystals will be in our basic geometric crystal, right? So this is geometric lifting of this very simple crystal I started with. So points are just vectors of, say, real numbers. And we have operators EIC, where I is the same indexing set, right? It just goes from, from 1 to n minus 1, I guess. But C's are now arbitrary real parameters as opposed to integer parameters. And I need to tell you how this thing acts on this vector. And the way it acts is the following. So EIC sends x1 through xn. And you can sort of figure it out from how the crystal operators act on this guy. So let me first write it down, and then I'll talk about it. So it does nothing to most of the x's. And then the i's x, it multiplies by C. And the next x, it's divides by C, and then everything else doesn't change. And you should be able to see why this is an action, right? So like what did crystal operator do over here when we act by EI on the piecewise linear single row? It just changes some i's into I plus ones or I plus ones into i's. So, and how many of them? Exactly as many as number of times as we act by crystal operator. Now, what does it mean changes? It means that one of those number gets bigger by C and the next one gets smaller by C, or the other way around. But now in the rational world, instead of addition, we multiply. So here, one of them gets multiplied by C and the other one divided by C. And all others don't change because, the number of, if we act by E3, the number of x1s doesn't change. Okay. Did this make any sense? I mean, ask me something. I think this should be possible to understand why this is lifting of the action we had here.
Yeah, I understand what you said, but I feel this is not really a perfect analogy. It's if you think
it's
the tropical.
Not perfect. Right, I agree. So, for example, one thing which is not perfect is that we had a cutoff, right? So, in the case of this here, remember I said, well, we can start with 1, 1, send it to 1, 2, send it to 2, 2. But if we try to apply it, it just dies. It gets sent to like 0 or something. But here you can, we can pretty much act with any C's, or you never. I guess as long as C is not 0, right? So as long as C is not 0. You can act with any C. So there is no cutoff. And there is something in the theory of Bernstein and Kazhdan which plays the role of this cutoff. It's called decoration function. And sort of the analogy, I don't know. Okay, I'll just say a little bit about it. So in the piecewise linear world, you have Schur function, which is sum over all vertices of the crystal. X in our crystal, I don't know how to do it, crystal weight of X, right? So in the what's it called? In the birational world, there is something called Whittaker function, which is the integral over our crystal of some kind of weight of with respect to some correct whatever measure. So what happens here is that telling you where to cut this crystal off, where things kind of, so to make it finite, right? To say that if you try to act after that, you just get sent to 0. Over here gets replaced by the following. You add a factor here, which is E minus decoration function of X. So in some sense, if the decoration function is very large, and that's just it's just some function you can compute for a point in your geometric crystal. So if it's very large, it makes this contribution very small. So instead of saying we forbid you to go beyond certain point, here you say, well, we allow you to go there, but actually your contribution will be really tiny. So something like this happens this notion of decoration function is the way Bernstein and Kazhdan came up with to deal with this issue of how to lift cutoff of actual Kashivara crystals. Okay, but let me just keep going here. Mm-hmm. This is analog of the basic SLN crystal. Now we can also, just like in the other world, we can extend it to tensor products. And it becomes a little bit more complicated. So here I'll write for you the formula. Let's say we are acting by crystal operator EKC on X tensor X prime, right? So we tensor product 2 of such things, for example, and X is a point in first one, and X prime is a point in the second one, and X times X prime is a point in the tensor product, and you want to know how this operator acts. So the answer is as follows. It splits this parameter C. It acts with some chunk of it, which we call C plus on X, and then it acts with remaining part CO plus 1x prime. Right, so we didn't see it in here because in this combinatorial world or piecewise linear world, we always only thought about applying each crystal operator once. So somehow our parameter C was always just 1. And then the way to split 1 into 2 non-negative integers is either 1 plus 0 or 0 plus 1. So that's why I told you that the crystal operator in the tensor product always chooses. It acts either on the first factor or the second factor. But in this case, you cannot do it as simply as that. You need to say that this parameter will split. And how does it split? There is a formula. So there is a formula which depends on those epsilon and phi functions, which I didn't tell you what they are, but it's a bit technical. So it's something like this. So C phi k x prime epsilon k of x divided by k x prime plus epsilon k of x. So epsilon and phi are certain functions associated to geometric crystal or even to the usual crystal. So when you define crystal, if I were to write, I can write for you, I have in my notes here, the actual rigorous definition of geometric crystal. I might do it in a little bit. I wanted to start sort of more with examples, but so I'll just explain by picture. So look, if there's two crystals, the way they can connect to each other is using epsilon and phi functions. Okay, so epsilon and phi, and here and phi. So, and here's another one, and it also has epsilon and phi, etc. So somehow, so those epsilon and phi functions, they don't matter much for what happens inside the crystal. In terms of if you act by crystal operators, those formulas don't involve epsilon and phi functions. But when you try to take their tensor product, then you need to be able to compute epsilon and phi functions here, epsilon phi functions here, and then combine them into something like this to know how to split your crystal operator, which part acts on the first factor and which part acts on the second factor. Okay, but let's now, so this was very general. Let's just see how it would work in our special case.
It may be one question.
Yeah, sure.
So is this formula for the how you split this formula? It only works for those one row.
This formula is for tensor product of any two geometric crystals.
Okay, any. Okay, I see.
This is very general formula. Yeah.
Not necessary for type A.
Not even necessarily for type A, I think. Yes.
Okay. Okay. Thank you.
It's what will change from crystal to crystal is how you compute those epsilon and phi functions. But this formula itself is always the same.
All right.
Okay, so let's see an example. We'll write down an example for you. Let's say we have, think of it this way. So let's say in piecewise linear world, we have two rows filled with 1s, 2s, and 3s, and we take their tensor product. Right, so in the geometric world, we want to encode those two things by two vectors, right? So let's call those, x11, x21, x31, and x12, x22, x32. And I want to arrange them in something like that will be helpful to. So in this example, to arrange them into just as a columns of a matrix. So I want to look at the matrix x11, x21, x31. So the first column tells me the first factor, and the second column x12, x22, x32 gives me the second factor. Right? So this encodes the point in my, now we think of it as geometric lifting of this crystal. And I want to know how, let's say, E1C acts on it. And here's the answer. It sends it to C1. So x11, C1 inverse, x21, x31, C2, x12, C2 inverse, x22, x32. Right, so far as that's what we've been expecting to happen, right? So if we act by crystal operator E1, it will somehow rearrange ones and twos here, but leaves the threes the same. That's what we see here, the threes are left the same. And how it acts, it actually just, if you act C times on the whole thing, it will act C1 times on the first factor, that's what this did. And it will act C2 times on the second factor, that's what this did. So it acts C1 times, the only thing which is missing now is I didn't tell you the formulas for C1 and C2. Okay, and I can tell you the formulas for C1 and C2. C1 looks like this. Cx12 plus x22 x12 plus x21 and C2 is C2 Cx21 divided by Cx12 plus x21. Okay, so as a formulas, and you can check that C1 times C2 is just C. You can check as expected, right? So the parameter C is supposed to split into two parts. Okay, so by the way, if you are taking notes, remember this example. Soon I will have exercise pertaining to this example. I mean, so I don't know, again, if you get bored during the next part of the talk. So, okay, any questions before I slightly move on? Okay, so now turns out that the energy function I was talking about can also be lifted into geometric energy. Which happens to be just some, actually it happens to be polynomial function. If you have, let's say, a tensor product, which is encoded by this array, rectangular array of variables, energy function is just specific polynomial in those entries. And soon we will see what it is in this example. But one property, so I want you to remember I was drawing those connected components. So now we are coming to sort of maybe the subject of this work, like what the paper is about. So remember I was drawing for you those connected components, and I said that, well, on the same connected components, the energy function is the same, right? 1, 2. What's the geometric lifting of this fact? It just says that once we write down the explicit polynomial for this geometric energy, okay, do you want me to write it down for you? I can write for you. So in this case, the energy function will look like this, x31. X22, okay, so it's just, this happens to be the correct function. And from which, by the way, you can find the tropical version too, right? If you just tropicalize this, you will have minimum of 3 sums, like this plus this, this plus this, and this plus this. And that's something you can find that explicitly allows you to compute energy function for such tensor product of 2 factors like that. Right, so you could just use this formula, tropicalize it, and then find energy of any tensor product like this. But anyway, so now in the geometric world, we have this polynomial over here, which is energy function. And the analog of this statement over here is that it stays the same when you act by crystal operators, right? So imagine that, I start at this point and I act by crystal operator, I end up in this point. Now I can compute this energy function at this original point, or I can compute it by plugging in those guys. Here's a puzzle. If you want to sort of, do sanity check for my talk, check just check that this explicit operator over here, right? I gave you explicit formula for this operator. Like each of those entries is some very specific function of the original ones and the parameter c. So check that now if you plug in those 6 things instead of those 6 things into this formula, you still get the same thing, right? You can, it's a small computation. You can check that this thing stays the same. In other words, energy function is an invariant of those crystal operators.
Would you tell us what is the geometric background for those energy functions? Do they live on some geometric object, say some regular function on certain objects? What?
So the sort of the body of your geometric crystal is a variety which is just a tuple of vectors like this. So it's just
okay.
So it lives I mean, you take rectangular array of variables, and that's where it lives. Sort of, it's
okay.
I mean, you could ask. I mean, in the piecewise linear world, energy function has some intrinsic meaning I was telling you about, which is that if you have some correct version of quantum group, which involves some kind of central extensions, and if you act by the central elements, and that energy function tells you how it acts, or something like that. So I mean, maybe what you were asking is that sort of, what's the meaning of this geometric energy? What is the meaning of this geometric energy function? And I actually don't know the answer, in the sense that for me, it's just correct geometric lifting of an important function in the piecewise linear world. Or it's possible that Bernstein and Kazhdan know the answer. It's possible that there is some intrinsic meaning to this energy function, but I'm not sure. I mean, in some sense, even the formula, even the polynomial formula for this birational lifting of piecewise linear energy is actually my result with Thomas Lamb. So it's sort of not that many people looked at it. So right, so just this formula, or more complex, more general case. So in some sense, it might be a bit of a mystery. And soon actually I will come to that. So soon I will say that, look, what I just told you is that this polynomial stays invariant under action of those crystal operators. So what we can do in our paper, we construct a whole family of polynomials which are also invariant under those crystal operators. And we call them pseudo energies. And so one of the big questions, in some sense, for which we don't know an answer, is that in what way is this energy special? We know it is special because it tropicalizes to correct energy here, but just without doing this tropicalization, without knowing that something here is special, how do we distinguish this particular energy from all other invariants of those crystal operators? And we don't know that. I mean, we don't know a good way to intuitive way to.
This looks very mysterious to me.
Right. Okay. So, but now you see, we are starting to approach sort of the question we were asking ourselves in this work, is that there is some kind of invariant theory happening here. We have a variety. In this case, it's a very simple variety. It's just a fine space with, dimension m times n or whatever. So, but you have variety. You have action of those crystal operators in this variety, which in general, by the way, is a rational action, right? So in general, if you just write some polynomial in those variables and you act by crystal operator, meaning you plug in those new values instead of the old ones, you will get a rational function. You will not get a polynomial again. So there is something, a bit of a miracle happening here, that this guy, even before you say that he stays himself, you could say, why does he even stay a polynomial? He could have turned into a rational function once you plugged in those things. So, so I mentioned that the puzzle is to just use this formula, plug it in, and check that this guy is actually staying the same. That I did this computation when I was preparing for the talk. It's sort of maybe enlightening to see. Just it seems a bit like a miracle. You just plug it in and it works out. Okay, so this was, and one more thing. So there is something called like GIT, geometric invariant theory philosophy, which says that if you have a group acting on a certain variety, then studying orbits of this group somehow corresponds to studying invariance of those action, this action. So in our case, it's not a group, right? Those crystal operators actually don't form a group. But nevertheless, you can ask something like that. You can say, well, let's say we have a crystal and we act by those crystal operators, and we want to know what are the connected components of this action, just like here. Like, for example, you could ask, is it really true that you can map any 6 parameters to some other 6 parameters by applying crystal operators E1 and E2 in this world? The answer is no. So, and one way to see the answer is no is that there are those invariants. There are things which you can compute of those as functions of those entries, which stays the same when you act by the crystal operators. And that's why if you have 2 points where the value of invariant is different, then of course you cannot connect them by those crystal operators. Okay, so, and it turns out to be sort of interesting and somewhat difficult question to say which geometric crystals are connected and which ones are not. So in our paper, we have some results like that, and we had to rely on some work of other people, and it was a very non-trivial thing to prove that some geometric crystal is connected. Okay, but let me keep going. So let me tell you the answer in this case. Okay, so let me tell you, we can describe the ring or the field of all, say, polynomial or rational invariants of those crystal operators acting for any, m and n, for any, dimensions of this array. So let me tell you how we would do that. So we have our array, which encodes, if it's m by n arrays, then it encodes, I guess, n factors for SLN crystals or SLM crystals, geometric crystals. And we want to know which functions of those parameters over here, which, let's say, polynomial functions, stay invariant when you act by those crystal operators, which seems, it's a very concrete problem, right? I mean, you could, like this computation I was suggesting you could try. It's a very concrete computation. Like, just you write polynomial in those things and you ask, well, if you plug in those new values, is it the same as it was before or not? So it's a very concrete question, but also those formulas are they're quite complicated. So it's not an obvious question. So here's how you can get generators for the ring of those crystal invariants. So out of such a array, we create matrices where we take, how do I say it? For each row of this thing, right? You take each row in this array. Note, by the way, that now we don't take columns, we take rows. So for each row, which looks something like this, xi1, etc. to xim, create out of it a matrix which looks like this. We put those on the diagonal, we put ones below them, and we put 0 everywhere else. And then take product. Take product of such matrices over all rows of the original array. So in this specific example, we would get, right? So this example, I would say this is an example where n equals 3 and m equals 2, right? So we are looking at SL3 crystals, and we take just 2 factors. So in this example, we would look at the product of 3 matrices, like x1, 1, 0, x1, 2, times No, x21, 0, x22 times x31, 0, x32. Okay, and now we just need to write down what this product is, and I'm slightly out of space, so I will erase this part. And in this case, the product, if you compute it, it will be just this. So it will be equal to x1, x1, x21, x31, 0, x21, x31, x1, x31, x22, x12, x22, x32. And we can actually make sense of all of the entries here. So what's x11, x21, x31? It's a product things here, which is geometric lifting of just the length of the first factor, right? So like what's like tropical version of this would be to add those three numbers, which is number of ones here, number of twos here, and number of threes here. So this product over here is a geometric lifting of just the length of the first factor. And similarly, this guy is just geometric lifting of the length of the second factor. And you would say, well, of course, if we act by crystal operators, we don't change the lengths of our factors. So those should clearly be invariants. And here it's just a coincidence, but in this case, this is an energy function I showed you. In bigger examples, it will not be like that. Energy function will be more complicated in some sense than the entries of this matrix. But the theorem says that entries of this matrix, so this is theorem of, well, of the people I listed on the board, that entries of this product, non-zero entries, non-trivial entries of this products generate, how shall we call it? So let's call it invariant, rational invariance of E intersected with polynomial ring, let's say over complex numbers of xij's, which is another way to say those are polynomial invariants of this action. That's the notation we use. Those are the rational invariants of crystal operators, and this is polynomial ring in those variables, so this is polynomial invariance. Okay, so this theorem says that once you create such a matrix, take this product, the entries will be exactly the generators of this ring of invariants. Okay. Any questions? Any questions so far? Like I might move on to, I mean, it will be related, but it will be slightly next topic. So anybody wants to ask anything?
Yeah, maybe a quick question. So here, there's an obvious symmetry that you can change the position of product, or say change the order of your tensor product, like R matrix. Is there some kind of symmetry?
That's what I'm about to talk about. So that's the next topic.
Great.
Yeah. So there is a R matrix here, which is non-trivial, something non-trivial. And by the way, here you could, well, anyway, let's just move on to R matrix. Okay. So let's talk about R matrices. So R matrix is a crystal automorphism. If you take tensor product of two crystals, say of the kind I told you, so crystal automorphism. If you take tensor product of crystal of length m of the kind I showed you, right? And another one of the length n, it happens to be isomorphic to if you did it in the other order. Right, that's sort of expected because those are supposed to model representations, and of course, if you have two representations of a group, then whether you tensor them in this order or that order, it's still the same tensor product. Now, for representations, the swapping of order of factors is trivial. If you have W tensor V, you can just map it into V tensor W, where little w, tensor little v, gets mapped into little v tensor little w, and this works. This commutes with the action of the group. However, it turns out that if you model your representations by those crystals, then it's still true that those two are isomorphic, but it's not true anymore that you can just simply swap the order of factors. Okay, so, and I actually prepared an example. Let me try to show you an example of this. So let's say we are taking one box tensor 3 boxes, and we will compare it to what we get if we tensor 3 boxes in one box. Okay, and here I will try to. The trick is to fit it on the board. So okay, so I'll try to do it like this. Okay, so let me write it here. So 1, 1, 1, 1. So I will skip some steps because it's very similar. We create this table, right? Rows, columns, and then the elements are Cartesian product of the two crystals. So in this case, the vertices will be like this. Or maybe I'll just write arrows right away too. 1 tensor 1, 1, 2. 1 tensor 2, 2. 1 tensor 2, 2, 2. 2 tensor 2, 2, 2. And then here we have 2 tensor 1, 1, 1. 2 tensor 1, 1, 2. 2 tensor 1, 2, 2, and that's it. That doesn't go anywhere. Right, so this is very similar to the example I had on the board before, right? So here we have just single box which can be filled 1 or 2, and this is 2 rows, and 3 boxes can be filled like 1, 1, 1. That's this column, 1, 1, 2, 1, 2, 2, and 2, 2, 2. So this is our set of vertices of this tensor product crystal over here. And the question is, how do crystal operators act? In this case, we are filling still with only 1s and 2s, so there's still only one crystal operator, basically E1. And that's how it acts. Those arrows show how it acts. It decomposes into 2 connected components, right? This guy and this guy. Now, let's do the same for the other order. Let me try. I'll have to erase it. Let's try to do the same if we multiply them in the other order. So in this case, it would look something like this. Maybe I'll write here 1, 1, 1 tensor 1, 1, 1, 1 tensor 2, 1, 1, 2 tensor 2, 1, 2, 2 tensor 2, 2, 2, 2 tensor 2. 1 to separate them. And then over here we have 1, 1, 2 tensor 1 goes into 1, 2, 2 tensor 1 goes into 2, 2, 2 tensor 1. Okay, so that's how we would assign those arrows for the same tensor product, just in the other order, right? If this length 3 factor was first. And you can see that really it's the same because it decomposed into 2 pieces. First one is just a chain of length 5, and the second one is chain of length 3. And you can see the same here, chain of length 5, chain of length 3. So hopefully you can see that those 2 are indeed isomorphic as graphs, for example, right? So it consists of 2 directed chains, one of length 5 and one of length 3. However, let's try to see how this isomorphism would work exactly. So for example, let's take the chain of length 3 over here and pick the middle guy. Okay, that's the middle guy in the chain of length 3. He beta correspond however we do this crystal automorphism, he has to map into this guy, right? That's the middle guy in this chain of length 3. But you can see that this is 2 and 1, 1, 2, and we didn't just swap them, right? We didn't just get 1, 1, 2 tensor 2. We got 1, 2, 2 tensor 1. So that's what I mean by saying that the product of two crystals is a way those are isomorphic as crystals, but this isomorphism is not trivial. You need to do something to this product to get this product. And whatever you need to do is this is called R matrix, right? So this is called R matrix. And it turns out that, well, at least in this case, in fact, more general for any rectangular shape crystals or Kirillov-Reshetikhin crystals, there's always unique map which swaps the two shapes, right? If you have two rectangular shapes, there is sort of unique map which from this crystal to the other way around, which swaps the two shapes. If you don't know what I mean by more general rectangles, don't worry. So in our world, what we need to know is that whenever you have tensor product of two crystals, right, like I was showing, like one of certain length and the other one of the other length, there is sort of, in fact, unique map which associates to a point in this tensor product, a point in the other way around, right? And this is called R matrix. And furthermore, it turns out it has the following very nice property. If you have a product of more than two factors, then you can kind of think of R matrix acting on this pair, R matrix acting on this pair, etc. And those satisfy our eyes, satisfy braid relations. Right. So you get a symmetric group action kind of where you say, well, I want to permute my factors by this permutation, and there is a unique way to do it. Okay, did this make any sense? Any questions? Okay, now let's try to lift this idea of R, this operator of R matrix to, by the way, matrix here is completely, I mean, it's not very good terminology. There's nothing matricy about it's a map from one tensor product to the other. So, but anyway, so let's see what is a geometric lifting of the R matrix is. Okay, so what is geometric lifting of R matrices? And it turns out that there's just a map and you can write explicit formulas for it. So let's go back to our example. So we had, this n equal 2, n equals 3, m equal 2 case, right? So x 1, 2, x 2, 1, x 2, 2. Turns out you can apply, so think of it as corresponding to having, again, tensor product of two rows, each filled with 1s, 2s, and 3s. So we are talking about geometric lifting of this crystal over here. So, and turns out that you can apply R matrix. There is such thing as geometric lifting of the map. You will get some new parameters. It's easier if I just give them names like this: y21, y22, y31, y32. And you can write explicit formulas for them. So here's explicit formula. I'll just write one of them so you can see how it looks like. y11 would be equal to x12 times Something like this. Hopefully I didn't make a mistake, but something like this. So there's, and then there's formula for all the rest of them too, which will kind of look similar to this formula. Which, by the way, again, you can use this birational formula. If you tropicalize it, you will get specific piecewise linear formula, and then you will know how to do R matrix on those guys. Okay. Now, once we have this thing, as I said, it turns out it again acts if you have tensor product, if you have m by n array, if you have more than 2 factors, then there's a symmetric group action kind of on columns of this array, right? So like in general, you would have like there would be like R1 swapping the first 2 columns or R2 swapping the next 2 columns, etc. So we could say that, I guess we would say that as M acts via R on our tensor products of our crystal. And again, it turns out that a lot of, so I didn't tell you last time, so many, so not just energy functions, there are many important functions on those geometric crystals, so which include epsilon phi function, decoration function, which I mentioned, energy function. There is something called, well, there is Nomi-Yamada geometric RSKs, right? So there is image of geometric RSK map. There is something called central charge. All of those things were invariants of crystal operators, but now I'm telling you that most of those things are also invariants of this R matrix action. So for example, the energy function, the same guy I wrote before, you can again check that if you apply this transformation, once you have all the formulas, he stays the same. So we can ask a very similar question. What are invariants of this action? And by the way, this immediately generalizes symmetric functions, because if you take SL1 crystals, which doesn't really make sense, but if you take SL1 crystals, meaning you have only one row, then you have just one thing in each column. And it turns out that in this case, our matrix action is trivial. It just swaps the 2 things. Right? If you have 2 rows filled with 1s and nothing else, just 1s, there's only one way to swap them, which is just you swap them. So in this case, so in SL1 case, the invariance of this action would be just symmetric functions. Right? But we ask this more general question: what is the invariance of this action? And let's see how much time I have. And we have a theorem about that too. We can describe, and in fact, this ring was first studied by Thomas Lam and myself. And we called it loop symmetric functions. So the theorem would be here that intersection of rational invariance with polynomial ring is generated by certain analogs of elementary symmetric functions. And I actually worked out like an example for you, but for the purpose of not running out of time, let me just maybe tell you the overall sort of, I mean, we kind of wrote 2 long papers. So I think now I can tell you sort of what the 2 papers are really about. So imagine that we have a rectangular array, right, just like before. So we have xij's over here. It has n rows and m columns. which somehow means that we have a geometric lifting of the tensor product, of SLN crystals, where we take M factors. I told you that there is an action of crystal operators, and the way it was natural to think about it is that crystal operators, EI, EIC, picks rho I and rho I plus 1 and does something to them, right? So I and I plus 1. So somehow it acts, they act horizontally on those rows. Like the fact that it just acts on those two rows, of course, corresponds to the fact that crystal operator here just changes the i's and I plus 1s, but doesn't change anything else, right? So there are those crystal operators which act like this. Now, I also introduced R matrix, which acts on columns, right? You can pick two consecutive columns and act on them by R matrix. And it's an interesting question, what this corresponds to in the usual crystal world. And well, in the usual crystal world, it's just you take two consecutive factors, right? And you apply R matrix to those two consecutive factors here.
Pasha, I suggest you might change a different marker because
okay, let me try a different story. Yeah. Yeah, unfortunately, they all are bad. Yeah, but okay, so, but can you see, so EICs act this way and R matrices act kind of this way. However, there's actually two more actions, because you can kind of transpose this array. You can act by crystal operators on columns, and you can act by R matrix on rows. And maybe to distinguish, let's give bar here. So let's denote. So it's a little bit weird, but there is such kind of obvious, in some sense, symmetry. You can just flip the array and act this way. And this does have meaning. People have studied this kind of dual actions in the usual crystal sense. They happen, for example, to commute, like those actions over here commute with those actions over here. And in fact, there is a bit of a surprise, because it turns out that the R matrix is actually a special case of a crystal operator. If you pick your two consecutive columns and correctly choose C, which will depend on the entries of those columns, then action of the corresponding crystal operator, kind of vertical crystal operator on those two columns, is exactly the R matrix I showed you. So it's a bit of a surprise. But now think of it as very analogous to the following, perhaps simpler kind of setting, where you just have an M by N matrix, M by N matrix. And on the left, you can act by GLM, or you can act by SM, which swaps rows, right? So, and on the right, you can act by GLN, or just by SN, which swaps rows, columns. And you can ask, well, we have those actions. We can choose either one of those four or some combination, and ask, what are the invariants of this thing? So for example, you could ask, what are the invariants of GLM cross SN acting on this thing? Right, so in this world, this would be like asking which polynomials of those parameters of this geometric crystal stays the same when we act both by crystal operators and also by R matrix. And the reason, part of the reason why the question is interesting is that, again, there are many examples. For example, energy function is just like what I told you. Energy function would live in kind of in this environment. So it would live in the ring of simultaneous invariants of this crystal action and this R matrix action, right? It has both of those symmetries. And that's actually what we call pseudo energies. So pseudo energies are certain elements of this ring of simultaneous invariants of those crystal operators and those are matrices. And then, basically I can draw for you a picture of what we know and what we don't know. So the picture would look something like this. Let me try. So here, let's forget the rings for a bit. Let's just think about fields of rational invariance. So there's just field of all rational functions in our variables xij. And inside of it, we can find invariance of R. And inside of it, we can find invariance of this E bar, right? Remember, I told you R is a special case of E bar. So if you ask to be E bar invariant, it's even stronger than asking to be R invariant. And here you have something like invariance of R bar, I guess, which contains invariance of crystal operators. And then here you get all sorts of invariance of both R and R bar, invariance E, something like this, it seems. Invariance of E and R. And finally, we have at the very bottom, you have invariance of E and E bar. So it turns out, so I can show you. So the part we can describe, we can prove actually what are the generators, etc., is this part. And those three things over here, we have conjectures, but we cannot prove them. So, okay, so that's one way to look what we can and cannot do. And the other one, in all of those cases, when we have, so for example, I told you that energy is simultaneous invariant of E and R. So it lives somewhere in here. We can have conjecture generators for this field/ring. We can write a formula for energy in terms of those generators. The formula is not conjecture, just the fact that those actually generate the whole field is conjecture. So what we noticed is that many of those things I named for you, right? So energy function, epsilon phi function, decoration function, central charge, image, the P and Q part of the Nomi-Yamada geometric RSK, all of those things have at least some of those symmetries, but the known formulas for them don't reflect those symmetries. So there is a formula for energy function, but so, for example, the formula Thomas and I found for energy function makes very explicit that it's invariant of R, but doesn't make it that explicit that it's an invariant of E. So another part of this project was to find formulas for all of those things which would reflect the symmetries they have. And it sort of, in this world, formula is kind of like I guess I'm trying to say that, for example, in the usual world, there's this important algorithm called RSK. So in this world, there's a geometric version of this algorithm called geometric RSK, but in some sense, this lifting is just a formula. It just tells you what the insertion and recording are in terms of original parameters. So in this world, finding a formula is sort of the key question you can ask about many things. Okay, and that's about it. I think I'm running out of time, so I'll stop here. Yeah.
So any questions? Actually, you are not running out of time. So
No, I have to take my kids to the zoo. So
yeah.
Okay.
Yeah.
Okay.
So maybe we have 5 minutes for question.
Yeah, please. So I probably should. I mean, I should have stopped in the middle to make a break since I didn't do it. Like maybe. So any questions about any of this?
Hi, maybe I have a vague question. So, do you have some ambitious expectation of this theory? So in the future, what do we expect it to do in some case?
So I can tell you what was the most ambitious expectation. So one of our most ambitious expectations was the following. So there are fundamental, complete homogeneous symmetric functions. And I showed you at the very beginning that they have like Q deformations, which are called whole Littlewood polynomials. So in this birational world, there are Whittaker functions, which are very important, right? So this, they should have a Q lifting, which would be like geometric whole Littlewood polynomials. And one of the goals of this project was to understand how to define them, how to write the integral, now taking into account this geometric energy function. Right? The difference between here and here is that here you have Q to the power energy. So here there is some integral which gives you this Whittaker function. So what we wanted was to write integral which would give a lifting of this of the Whittaker function, the Q analog of Whittaker functions. And so far, so part of what we did actually answer. So when you write this integral over here, I showed you that one of the things you have in there is Q to the e to the decoration function. So we know how to take care of this term because we know we wrote so one of the results in the paper is explicit formula for this. Whatever it's called, decoration function in terms of whatever we needed to write it in terms of. However, our biggest problem, I guess, is that we don't know, or we got stuck with the measure. Like you need to integrate over a certain measure, and we just couldn't figure out how to make it work nicely. So this was one of the ambitious goals, to write geometric lifting of whole Littlewood polynomial, right? In the same way as Whittaker function is geometric lifting of actually, of this thing. So I guess I should probably put Schur function here. So Whittaker function is really geometric lifting of S lambda, but you can still ask what is geometric lifting of whole Littlewood, and that's what was one goal. Another goal was,
I'm not very familiar with the Whittaker function, so maybe you can say a few in a concise way. What do you mean by a Whittaker function is a geometric lifting of Schur function?
So Whittaker functions, I think they came from number theory, and I'm actually not a big expert in it. But the idea is that you can write Schur function as a sum over all semi-standard Young tableaus. So it's a which you can think of as summing over all elements of certain crystals, the weight of this element. So
I heard about those people working on those multiple the zeta values are interested in those Whittaker functions.
That's right. So there was recent interest to Whittaker function, even though they come kind of from number series. There was recent interest from like probabilists and things like that. So I forget so Ivan Corvin would be the one name of a person who works in this direction. But basically, they figured out that certain functions, which they already knew, which existed kind of and played some important role in some theory, you can write them as integrals over certain geometric crystals. Right? So this was kind of, I guess, unintended application of this Bernstein-Kazan series. When they were writing their series, they didn't know that this will be the case. But so it turned out that Whittaker functions can be written as integrals of certain geometric crystals, which are not too far from the crystals I showed you. And then there are how do I say it? There are certain integrable models where those Whittaker functions are eigenvalues or something like that. And then you could ask, well, do those models have Q deformations where you would have those geometric whole Littlewood polynomial as their eigenvalues. Or yeah, I guess eigenvalues of some important operators. So, but yeah, sadly we don't know how to do it. So if we knew, I would tell you. But we made some partial progress, but we didn't solve the whole problem.
And you know the energy function living this E and R invariant, and you find all the generator for those E R invariant, but they still cannot tell what is special about those energy functions.
That's right. So that's the other thing, is that another goal, at least I had, is try to understand what's so special about this one particular energy function compared to all others. So you can define those other ones, and which are, by the way, in some sense, energy function is also a sum of semi-standard Young tableaux. There is like a formula for it, which it looks like a Schur function. It's like it's basically some variation of a Schur function of specific shape. So if you take different shapes, you can create more elements in here, and then you could even go back. You could tropicalize them, and you could grade your tensor products of your representations by value of this tropicalization. So it will give you some other Q analogs of H lambdas different from Littlewood. And you can ask, well, why is H lambda so natural? And so like, I guess there are many reasons why H lambda is so natural, but you could ask, like, I guess, are those other ones interesting from any point of view? Do they have any of the properties that H lambda has? Anyway, so that was another. So, and the third one is the question of connectivity. So, so decomposing a crystal into connected components is actually something important, right? That's what originally you do. That's how crystals allow you to solve the problem of taking tensor products of representations, right? You take two connected crystals, you take the tensor product. It turns out that it falls apart into connected components, and so then the way it falls apart into those connected components is exactly the same way as tensor product of those two corresponding representations decomposes into irreducibles. So, but then interesting things start happening. So, for example, you can define also a affine crystal operator, right? I didn't talk about it, but you could have one more crystal operator, E0, which is a affine one. And then you could look at things. So from that, in the affine world, the only shapes which make sense are rectangles. And something interesting happens here, because as an affine crystal, tensor product of rectangles is actually connected. It's a single kind of irreducible representation of this affine quantum group. But as classical one, it decomposes into irreducibles. So one question which sort of, at least I was asking myself, is that it's possible in this whole geometric story to also define the action of the affine crystal operator. And then the most basic question is it true that this tensor product of those basic geometric crystals, like this area over here with those, plus with the additional E0 which acts on them, is it true that this thing is connected? This would somehow correspond to creating irreducible models for this modules for the quantum group, for a affine quantum group, by tensoring the rectangles. And we don't know the answer. I don't think we know the answer. Conjecturally, it is connected, but it's completely a non-obvious how to.
Okay, so let's say like in type A, this is Kirillov-Rishtikin's. This is right. the square, the squares. But what about the other type? What will be the shape to working with for other types, say type D or E?
Oh, I don't know. We haven't tried that. We are mostly been working in type A. But even for Kirillov-Rishtikin crystal, so I told you how to lift to geometric world a single rock crystal. If you want to lift to a geometric world a rectangle, it turns out to be like 1 degree more difficult. So one of the courses, Gabe Frieden, his PhD thesis is in some sense on how to do it. And it turns out to be, so you somehow need to use certain parameterizations of Grassmannian to do it. It's related to this Postnikov theory of totally positive Grassmannians and
Mhm.
things like that. So it's a highly non-trivial question. So like in some sense, a single row thing is very basic, but once you try to live to geometric world, arbitrary rectangle, it becomes quite complicated. For example, writing down explicit formula for R matrix, quite complicated. Okay, thank you. I have to run.
Sure. Sorry. Okay.
But thank you so much for coming.
Thank you very much for the nice talk. Yeah, we learned a lot.
Thank you for inviting me.
All right.